I'm not a biochemist. I'm actually an electrical engineer, and I wanted to give a brief overview to everyone here about some of the remote sensing and other space applications that we're working at GTRI in collaboration with a few of the schools at Georgia Tech. So this is an outline. So first I'll provide a brief background about Georgia Tech and their space history. The bulk of my talk is going to focus on this MicroNimbus IRAD, which is a remote sensing CubeSat for measuring the temperature in the atmosphere. And then I'll wrap up with some other applications that we've done and take any questions that you may have. So some of the history of GTRI. So back in the 80s, we worked with the Long Duration Exposure Facility, which was about a bus-sized satellite in space, and it was meant to have several experiments to see the effects of low Earth orbit, and particularly radiation, on those experiments. Some of them were biological, some of them were electrical. In the 90s, we worked with the International Space Station and worked on their airlock antenna. And you can see right here, you see a astronaut, and the antenna actually is built into the handle here, and it's what they use to actually communicate with their fellow astronauts in the space station when they're coming through the airlock. As I mentioned, the focus of my talk will be on these current projects we're working at, primarily that MicroNimbus CubeSat. Before we go into the actual engineering behind MicroNimbus, I'll give you an outline of what we were talking about when we were looking at a remote sensing radiometer. Mm-hmm. Yeah. Okay. So what we're doing is we're focusing on the 60 gigahertz RF spectrum. And what we see here on the right-hand side is attenuation or absorption of electromagnetic radiation against frequency for oxygen. And normally oxygen has very fine lines in its absorption spectrum, but at lower altitudes we actually see a broadening due to high pressures in the lower atmosphere. But as you go higher up, you actually start to resolve these different transition frequencies. And what we can do is, because of that, we can actually focus in frequency and bandwidth of our RF system, and we can actually tune to one of these transition frequencies, and we can probe along it. And by doing that, you can actually focus in a certain area in the atmosphere and gauge its temperature. So by doing that, we worked off of a previous thesis from MIT by William Lenore, and he provided that if you chose certain frequencies and bandwidths across that spectrum, you could resolve these weighting functions or windows. And basically, if you choose these RF frequencies and bandwidths, you're isolating your measurement to this, like an isothermal slab in the atmosphere. So you can actually focus and measure the temperature of that slab of the atmosphere. And by changing that, you can actually walk across these frequencies. And we've actually optimized that to account for our equipment. And we see we have 7 window functions. So as we're flying over the low Earth orbit, we can actually scan across these different frequencies and measure from about 10 kilometers up to 70 kilometers and give a very large depth profile of the atmosphere for weather radars and other applications. So I don't know how many electrical engineers are here, so I won't go too deep into this. But one of the big novel aspects of this system was that we took a board level or a radiometer that uses commercial off-the-shelf parts, and we actually integrated everything into a single chip. So what we see here is a receiver that would use in a radiometer where we have an antenna that's pointed down at the Earth. We have on-chip calibration, which usually is a fixed load at a certain temperature that we can switch to and calibrate our receiver channels. And then we have amplification and down conversion that lets us select a certain frequency, and then we pass it on to a filter bank that can select our different bandwidths. To do this, we collaborated with my former advisor at GT Electrical and Computer Engineering, the School of Electrical and Computer Engineering, Dr. John Kressler, who are leaders in the silicon germanium research efforts and can design these type of applications on a single chip. We chose silicon germanium because it provides some performance compared to 3.5. It's cheaper. You can integrate digital. You can bring everything down to a single chip. It has excellent one-over-F noise, which, if you don't know what that just means, is that it provides a good long-term stability in these systems. And it's radiation hard, particularly for low Earth orbit and even up to the Jovian atmosphere. So this is what an integrated radiometer looks like. I won't go down too deep, but the biggest things I want to talk about is that it's very small. You bring that whole receiver channel down to a single chip. It's about 1 millimeter by 2 millimeters. And you can see here the power draw is only about 81 milliwatts. So this is a perfect system for CubeSats. CubeSats are very limited power distribution systems, and they have very limited power, battery banks. So we really need to reduce the power requirements. This slide here shows some of the metrics. All I'd want to convey is that this is comparable to the state of the art in terms of some of the other systems coming out of MIT Lincoln Lab or NASA or JPL. And it allows us to resolve those temperatures down as we need to. And we're actually working to reduce this noise figure. This is a limiting factor in how fine we can get down to a temperature measurement. We're trying to bring that down to our new final system. Now, the previous slides showed some of that, the diamicrograph of that receiver. What we're seeing now is the full integration. So now we have everything we need to look at 60 gigahertz, measure the atmosphere, bring it down to our IF frequency so we can actually digitize it and beam it down to Earth. And now we're including everything we need to generate the local oscillator frequency, what we need to actually downconvert. And everything fits in about 2.5 by 3 millimeters squared, so it's very, very small. So in terms of the actual payload, we're working with Professor Glenn Lightsey from the Aerospace Engineering Department, and to help go through this, I actually brought a 1-to-1 scale model of MicroNimbus. So if you don't know what CubeSats are, they have a standardization. So a 1U is a 10 centimeter by 10 centimeter by 10 centimeter volume. And it has a weight requirement as well. It's about 1.33 kilograms, or about 3 pounds. And this is a 3U spacecraft. So it's 10 by 10 by 30 centimeters. You can see here, we could break into 3 sections. The lower section, which will be on this side, is our payload, and that's where we actually have a radiometer and all the electronics we need. You'll notice here we see a cone that's actually a horn antenna, which is right here. This is the actual size of what it would look like. This alone had a lot of engineering behind it, because normally to get the performance we need, the beam widths we need to scan, because we're resolving down to about 50 kilometers swath on the Earth's surface from low Earth orbit. Normally they're 3 times longer than this, which wouldn't fit in a CubeSat. So we re-engineered this and we got it to fit and have the weight requirements to not push over what we need. If we move over, we'll see the other 2 modules, which is what Dr. Glenn Lightsey has led. First of which was the attitude determination and control. So that'll be this upper module, and that has our sun sensors for kind of getting us our bearing and all of our torque rods and reaction wheels we need to detumble and control the satellite as it's orbiting the Earth. We also have the service module, which will be the center region, and that has our electric power system, our GPS unit, our command and data handling unit. So all 3 of these are integrated together to build this. And now this gives you a view of how this would work. So we launch up. We actually go to the ISS. They actually have a CubeSat launcher on the ISS, and they can just send these out in their low Earth orbit. When we come out, we detumble. We get in a stable orbit, and then once we power up and we're in our nominal operating regime, we start scanning the Earth's surface. We have to do all our measurements in about 7 seconds, because after 7 seconds you pass over 57 kilometers or 60 kilometers. So we have to do all our measurements very quickly, digitize it, and then as we move across, we'll scan again. As we approach and we get in line of sight of Georgia, we actually have a ground station, which I'll cover shortly, and we'll start communicating and getting our telemetry corrections and also beam down our data so that we can actually look at it and share that with scientists as needed. So that covers MicroNimbus. I wanted to touch base on a few other space-related work that we've done. So I'm part of Space Systems Program Office, which is under the Advanced Concepts Lab, and they have experts there in electromagnetics, particularly with antennas. And one of the big things that they've done is develop these fragmented radiator technology. And what that is, they have these custom in-house algorithms that can take in and work with scientists or engineers, and we can design this antenna element for very precise performance, be it bandwidth or frequency, or maybe you want to cancel out some interference. We can design very large panels, and we can integrate that with all the power divider and everything else behind that feeds into the antenna, and then that can feed in right to our satellite. You can put it out outside. It's easy to space qualify these antennas, so it's really easy to bring this into space-related applications. And for example, one of the projects that we're working on is called Skyfall, and this is not a CubeSat. This is actually a small set. It's about 150 kilograms, if I remember correctly. And what we designed is this large phased array antenna. Has about 8 panels, and what you can do is you can build lots of these antenna apertures, as I mentioned, and you can scan the beam. You can electronically point the beam as it's orbiting. And this application had a 1 meter resolution at a 500 kilometer orbit, so it's very fine. So now that covers some of the projects that we've done. Georgia Tech and GTRI specifically is investing in some facilities to work for our projects, but also eventually working with any scientists or future projects. One of which was repurposing this clean room. It's actually in Baker Building, which is on Dolney Street, kind of just a 5-minute walk away. It's a Class 100 clean room, and we're repurposing it as a spaceflight assembly area, so we could actually build payloads in a clean environment, qualify them, and send them out. And one of the really cool things that we've installed is this ground station. As I mentioned before, it's MicroNimbus is orbiting around the Earth and measuring. We need to beam that data down. So we installed this ground station. It's in Cobb County. It's actually, I think, going to be near Ironmonger, I think, actually. There's a facility there.
It is.
Yeah. And with that, we'll be able to communicate with our satellite and get our data and share with scientists. But also, we're working with other engineers and other scientists to use this facility for other programs. So I hope that provided you with a good outline of what we do. Again, this is kind of the engineering side. We really love building these systems, but we need to talk to scientists like you because you're the ones driving these missions. So with that completes my talk, and I'll take any questions.
Question of two?
Yeah, that was really cool. So, are you? I think I got that you're doing single point measurements. It's not scanning measurements.
For MicroNimbus, it's like it has an 8-degree beam width. Yeah, it's fixed. But for some of the applications, we have a phase array.
But you said you have to do the measurement all at once, and it takes 50.
7 seconds. So yeah, as it's moving across, it's pointed at nadir.
Right. So it's just doing a single point measurement.
Yeah, and it's scanning across.
You're not scanning. You are scanning.
You are scanning. Yeah, well, you're taking 7 seconds. You're taking the measurements, digitize it, and as it passes into the next swath, you take another measurement until your memory's filled, and then you'll dump that and then go again.
Okay.
Yeah, and the idea is to make this cheap enough that you could launch a constellation of these, and then have a real-time 3D map of the Earth's atmosphere.
And is that the actual, or is that just?
This is what it would actually the size would look like. The 3D printing does not do great on the panels. They would actually be flat and they won't be warped like this. And you might have noticed these whip antennas. Those are a UHF, and that's for telemetry. Yeah.
Okay.
I guess my question was answered, but I was thinking the temporality of the measurements, but yes.
Yep.
I was just wondering if you had any mass constraints on your design, or if it factored into any of the selection of your components, because I know for designing CubeSats, NASA usually has some restrictions on mass, or not just size.
Oh yeah, and by mass, you mean
like weight.
Weight. Okay, yeah, that is a big thing. So in terms of the actual CubeSat itself, the AE department, we try to go as lightweight as possible. Since we're in low Earth orbit, shielding is not a big constraint. My background actually is in radiation effects and these electronics, so we can go light on that. In terms of the antenna, by shrinking it, we were able to save weight because it's actually a little heavy. It's actually copper, solid copper. But that makes sense. For example, I'm designing. We're still finalizing some of the board level components for doing the digitization, and we have to be careful about how many layers those boards are. Any mass matters, but we always add like a 20% margin of error, so that worst case if you go over, you're still well below the limit of those launchers. Yeah.
Is the speaker one more time?